So this series of videos are for my Math 103 college algebra course at Central Connecticut State University. And I'm going to kind of walk through the notes as I would give the lecture in class. For my class, this can be used as a resource. If you missed class, you could use this to catch up. If you're doing this on your own, welcome. And I hope that you get something from this video. In this first video, we're going to look at just numbers, the background of numbers, data, problem solving. And we're going to start with looking at the various sets of numbers, the natural numbers, the whole numbers, the integers, rational numbers, irrational numbers, real numbers. The set of natural numbers is also sometimes called the set of counting numbers. Okay, I hope you can read my handwriting. The set of counting numbers, this is the basic use of numbers. The numbers are basically used for counting. That is their first purpose. And so the set of natural numbers would be the set of numbers 1, 2, 3, 4, and so on. The numbers we're used to. How many people are in the car with us? 3. How many cups of coffee did I drink today? 2, 4. You'll notice that the set of natural numbers does not include 0. It does not include negatives. It does not include decimals. It's just the series 1, 2, 3, 4, 5, 6, 7, 8, and so on. The set of whole numbers then is different only in that the set of whole numbers includes 0, 1, 2, 3, 4, and so on. The set of integers, now we include some of the negatives. A lot of people say that the integers is the set of whole numbers as well as negatives, natural numbers and the negatives, which is not exactly true. The set of integers is the set of whole numbers and their opposites. So where we do have 0, 1, 2, 3, 4, and so on, we also have -1, -2, -3, and so on in the opposite direction. Notice that we do not have fractions. We do not have decimals. The set of rational numbers is now the first time that we're going to introduce fractions. And a lot of people say that rational numbers includes fractions. Rational numbers, however, is things that are a quotient. Whoops, a little crazy there. A quotient of two integers. Rational numbers is numbers that can be expressed as a quotient of two integers. That would be like 4 over 2 is a rational number, which of course is equal to 2. 3 over 5 is a rational number. 7 over 2 is a rational number. Those numbers are rational numbers because they can be expressed as a quotient of two integers. 0.3 repeating. It's a decimal, but it's also a rational number because it can be expressed as 1/3. So some decimals can be expressed as a quotient of two integers, and so they are considered rational. 0.5 is 1/2. Any decimal that will either end like 0.5, 0.25, 0.6, those numbers are rational. They can be expressed as a quotient of two integers, a fraction where both the numerator and the denominator are integers. Any decimal that will repeat, like 0.33 repeating, that can be expressed as a quotient of two integers, in this case, 1/3. In irrational numbers, a number that can't be expressed that way. So an irrational number might be the square root of 2, pi. Any decimal that neither ends nor repeats is an irrational number. In the math that we do, particularly in this college algebra course, the most common irrational numbers we're going to see are the numbers that are square roots of non-perfect squares. So, for example, the square root of 4 is not an irrational number because that equals 2. So that actually is a natural number, even though it has the radical. Okay, real numbers are the collection of all numbers, whether rational or irrational. So if I go back up here, the natural numbers, let me use a different color. Natural numbers, whole numbers, integers, those are all rational numbers because they can be expressed as a quotient of two integers. Like 4/1 is rational, that's a natural number. Irrational numbers are numbers that are not rational. So all of the rationals plus all of the irrationals, those numbers combine to give us the set. Those numbers combine to give us the set of all real numbers. Got a little messy there. So here's just some examples. 3 is a natural number. It is the most basic set. 0 is not a natural number, but it is a whole number. 3/7 is a rational number because it can be expressed as a quotient of two integers. 3 and 7 are both integers. But because it doesn't divide evenly, it's not an integer. Because it's not an integer, it's not a whole number, it's not a natural number. The square root of 15, 15 is not a perfect square, so this is irrational. -6, it is a rational number, but it's not a whole number because it is a negative. So -6 fits in the group of integers. I might suggest that you pause the video, try 6 through 10 on your own, and see what you come up with for each of those. If I work through 6 through 10, the square root of 64 is 8. 8 itself is a natural number or an integer, is a natural number or a whole number. The opposite of that, -8, is going to be an integer. So I'm working through the smallest group that these numbers belong to. Now you'll notice that number 7 is a fraction. It is a quotient of two numbers. So I'm tempted to say that it's rational, except that the square root of 3 is not a rational number. So the square root of 3 divided by 2 is irrational. 1.56, it is a decimal, but I could write that as 156/100. That is a rational number. So 1.56 is a rational number. Any decimal that ends or repeats can in this way be written in, that ends can be written into a fraction this way. A number that repeats, like 0.371, because it's 3 digits in the repeated pattern, 371 divided by, not by 1,000, but by 999 will equal that 0.371 repeating. So if you check that out, try that with a calculator, you'll see that that number is also rational. -2/5, because of the negative, I might be tempted to say it's an integer because that's where I talked about the negatives, but 2/5 is a quotient of two integers that's not an integer by itself. So this, again, the smallest group it belongs to is the set of rationals. So that's just a little bit of an introduction into the types of numbers. Order of operations is something from early in mathematics. We typically see this in elementary and middle school. However, it's a good thing to review. Okay, you may have seen what a lot of people refer to as PEMDAS. I get a little nervous about that. First, you look at parentheses and then exponents. Multiplication and division, you do not do multiplications first and then divisions. You do the multiplication and division from left to right. The same thing with addition and subtraction. This is what makes me nervous about PEMDAS, is that we tend to think we do all the multiplications, then all the divisions, then all the additions, and then also the subtractions. You do all the multiplications and divisions, but you go in order from left to right. The same thing with addition, subtraction. You go in order from left to right. So number 11, the first thing I'm going to do here is inside the parentheses, I'm going to do the multiplication. So I have 16 minus 15 So I have 1 inside the parentheses. Negative 2 divided by 2. I'm sorry, negative 2 times 1 divided by 2. I do this multiplication first. So negative 2 divided by 2 is negative 1. We need to be careful that we do these in the right order. Number 12, I'm going to start in the parentheses. 4 minus 5 is negative 1 squared. Now notice that negative 1 is in the parentheses. You want to be very careful that you square the negative 1 and not just the 1. Here, 3 squared. I have minus 3 squared. That's in a parentheses. That's a pretty ugly parentheses. Let me try to make that parentheses again. That 3 squared is in parentheses, so I have minus 9. The square root of 9 is 3, so that's minus 3 times 3, so that's another minus 9. Negative 1 squared is negative 1 times negative 1 is a positive 1. Minus 9 is minus 18, and 1 minus 18 is negative 17. So you want to be very methodical with your order of operations. In number 13, I have 6 minus, now I have 4 squared. 4 squared is really a multiplication, so I do that multiplication first. 4 squared is 16 divided by 2 to the third. 2 to the third is 8. I'm going to keep going with just the numerator for a little bit. So I have 6 minus 16 divided by 8. I do that division before I do the subtraction. So 16 divided by 8 is 2. Again, sticking with just my numerator, 6 minus 2 is 4. Go back and work at the denominator now. 3 minus 4 is negative 1. I'm going to carry that down and carry that down. 4 divided by negative 1 is a negative 4. Okay, so this is just a quick look at order of operations. Percent change, this is going to seem to come like, how is this related to everything we've done before? And it kind of is, in that we're working with basic numbers. Also, it's something else that we're going to look at in this section here. Percent change. I have some pretty crazy numbers here. Steve and Lisa bought their house in 2010 for $178,000. Today, their home is valued at approximately $250,000. What's the change in value of their home? Okay, let me scroll down, find some empty space, and let's look at a little bit easier problem. Let's suppose that you buy some collectible for $200, whatever it is. You buy a college algebra book. You pay $200 for it. Hopefully it doesn't cost that much, but you pay $200 for your book. At the end of the semester, you decide to sell that book, and you sell it for $250. Wouldn't it be really nice if it worked out that way? Was there an increase in the value of the book? Okay. The amount of increase. I hope you can read my writing a little bit. The amount of increase is the sell price minus the purchase price, or $50. The value of the book increased $50. Now, what was the percent increase? To find the percent increase, I'm going to find that difference between the sell and the buy, and I'm going to divide that by the buy. So in other words, my price increased $50. 50 divided by 200 is 1/4, or 0.25, or 25%. So the increase, the percent increase in the value of the book is 25%. The amount increase was $50. The percent increase is 25. So if I go back to Steve and Lisa, they bought their house for $178,000. Today, it's valued for $253,000. So we have, again, here's my buy, and here's my sell. So if I do $253,000 minus $178,000, we see that the value of their house increased by $75,000. So the change in value is the $75,000. Put a dollar sign on there. The percent increase, not only do I want to do the 253,000 minus the $178,000, which we said is 75,000, but what percentage of this, what percentage of the buy price, the original value? So while the original value was $178,000, increased $75,000, what percent is that? If I do 75 divided by 178, I get a decimal of 0.421. I'm rounding to 3 decimal places. So that's approximately 42.1%. Let me clean that up. So that's an increase of approximately 42.1% increase, and so that's their percent change. Okay. So here's a case. Recently, 2 governors were discussing the increase that their states had seen in the number of cases of a certain illness. January 1st, State A had 250 cases. State B had 1,500 cases. On June 1st, State A had increased to 350 cases, and State B had 2,000 cases. Which state saw a greater increase in cases? This is something that we'll argue about. When I say which state saw a greater increase in cases, what do I mean by increase in cases? Do I mean the number of cases or the percent increase of cases? So let's look at State A. Okay, State A, on January 1st, had 250 cases, and on June 1st, had 350 cases. So for State A, 350 minus 250, State A had an increase of 100 cases. State B, on January 1st, had 1,500 cases, and on June 1st, had 2,000 cases. So State B went from 1,500 to 2,000. That difference is 500 cases. So State B saw a larger increase in the number of cases than State A did. So if I'm the governor of State A, I'm going to say, hey, State B, you had a greater increase in the number of cases. What are you doing about that? However, if I look at the percent increase, State A, that difference of 100, right? That 350 minus 200 gave us the 100. If I divide that by the initial value of 250, so 100 divided by 250 is 0.40 or 40%. So State A saw a 40% increase in the number of cases. State B, again, the difference from 2,000 to 1,500, we said is a 500 case increase. However, they started at 1,500 cases. 500 divided by 1,500 is 0.33 repeating, or 33.3% increase. So this is a case where people can argue, right? Who had the greater increase? State A is going to argue State B had the greater increase. State B is going to argue that State C had the greater increase, depending on whether I'm comparing the number of cases or the percent increase. Okay, so you want to be able to compare both. So that's why question A, which state saw a greater increase is a bit ambiguous because are you talking number? Are you talking percent? And really, little opinion here, editorialization. My argument would be you should always include both in your conversation. All right, so just a little bit of application here. The volume of a cylindrical soda can is given by V equals pi r squared h, where r is the radius, h is the height. So if I say volume equals pi r squared h, where r is 1.3 and h is 4.4. So I have pi times my radius, which is 1.3 squared times 4.4. So I'm going to use my calculator, and hopefully you're good with the calculator. In my subsequent videos, I'll link in a calculator as well. But I'm going to do pi. You might be able to hear my calculator buttons getting pushed here. Pi times 1.3 squared times 4.4 is 23.36. Radius is measured in inches. Height is measured in inches. Radius is being squared, so that's going to be cubic inches. My volume is 23.36 cubic inches. Can this can hold 23 fluid ounces? Well, what I want to do for this, I don't want to convert cubic inches into fluid ounces. Here's the best way I think to do this. 23.36 cubic inches. I'm going to set up a little fraction here. 1 cubic inch equals 0.55 ounces. The reason I chose to put the 1 cubic inch on the bottom is because now my units, cubic inches, cancels. And if I multiply 23.36 times 0.55, my units will be the ounces, and 23.63 times 0.50. Oops, I'm going to back up here. I reverse this at a moment. 23.36 times 0.55 is 12.848 fluid ounces. So can this can hold 12 fluid ounces? The answer is obviously yes, I can. So that's the first evening, this first set of notes for college algebra, Math 103 at CCSU. Thank you for listening.